Hey, Calc kids, today we're looking at section 3.2, the differentiability of a function. Notes out, and away we go. So we're looking at differentiability, i.e., where is a function differentiable? So we're gonna look first at where is a function not differentiable, and by that we can say, where is a function differentiable? So where is a function not differentiable? Well, it's where the slope changes drastically. So it turns out a derivative only likes nice, easy curves, nice slow ski slopes. It doesn't like jumps. It doesn't like points, things like that. So it wants a nice, easy curve. So there are 4 places where the first derivative might fail to exist. The first one is at a corner. And for example, we'll look at the absolute value f of x. We looked at that in a previous lesson. So at 0, we get a corner, and we know from our previous example, the derivative changes from -1 to +1. There's a jump, there's a discontinuity in the derivative graph. Therefore, a corner is not good for differentiability. Right? We looked at that graph earlier, f of x, open, solid, open. So when we look at the first derivative, there's actually a discontinuity in the graph of the first derivative. And the reason that caused that was that corner. So we want to avoid corners. Another thing we want to avoid are cusps. If we look at a graph of f of x equals x to the 2/3, we actually get a function that looks like this. It looks like a bird flapping its wings. But it's that same idea as a corner. A cusp, again, is going to have a drastic change in slope, causing a discontinuity in the slope graph. A vertical tangent will also be bad for differentiability. And for example, if we look at f of x equals the cubed root of x, and I didn't write that cubed root in there, the cubed root of x, we actually get a vertical tangent. And so what that looks like is if we look at this graph, we get a graph that looks like this. And it's really hard to see, but right here in the middle, the graph of the first derivative then actually has a vertical tangent, because right at 0, it has a graph that's almost infinite, and then it's getting slower and slower to 0. If we look at negative, it's got a negative slope. This is a negative slope, and it's going to go the other way. And so there's a graph that has a vertical tangent. And so vertical tangents are bad for differentiability. And finally, discontinuities. So for x is -1, for x less than 0. Again, this is our function, not the derivative. And 1 for x greater than 0. Again, there's discontinuity. Therefore, if we looked at the slopes, there would be a discontinuity. So again, bad for differentiability of a function. Most functions are differentiable and do not contain corners, cusps, vertical tangents, and discontinuities. But even if they do, we can still look at what's called locally linear. So if you zoom in close to x equals a, the curve will straighten out and resemble its own tangent line. So for example, we're going to look at the function y equals 2 to the x, exponential growth. And so if we look at that general function, y equals 2 to the x, y equals 2 to the x, we get a graph that looks something like this. Has to go through 1, 1 it's 2, 2 it's 4, and there's our exponential growth. And if we zoom in several times at x equals 0, we want to see what happens. So zoom in. And I'm going to zoom in again one more time. But the idea here is if we keep zooming in, then that curve starts to actually straighten out. And I lost my window. And I did the wrong one. But anyways, keep zooming in, right? If we take slices and keep zooming in, that curve gets straighter and straighter. So we can actually find the derivative on the calculator that uses a symmetric difference quotient to approximate derivatives. And we're going to look and see what that means. Find the slope of the tangent between a minus h and f of a minus h and a plus h and f of a plus h. So our slope then, so now instead of just adding an h value, we're also going to subtract a value. And we're calling this the symmetric difference quotient. So we're going to subtract, again, just slope, y2 minus y1 over x2 minus x1. And we have f of a plus h minus f of a minus h all over a plus h minus quantity a minus h. And what we're going to get is f of a plus h minus f of a minus h all over. And then what happens? We get a plus h minus a plus h minus the negative. The a's cancel, and we actually get 2h. And so this is actually the formula the calculator uses to find derivatives. The calculator uses an h value of 1 to the 10,000ths. And so let's look at sketching a picture. We're going to use y equals our 2 to the x function. And so let's go back to our curve. And let's say we want to pick a value that x is 2. So we're going to look at x is 2. And then I'm going to blow this picture up a little bit so this makes more sense. So if h is 0.0001, then plus h is going to kick us out to 2.0001, and subtract h is going to make us 1.9999. And so if we plug in those values into our calculator, and let's see what that's going to be. So we have 2 to the 1.999. We're going to get a value of 3.9997. 2 we know is 4, and 2.00, 2 to the 2.0001 again gets us 4.0003 or 27. All right, and so the calculator then would use that value then to find the derivative, again using slope function. We can also do this using your calculator. Find the value of the derivative of f of x equals the function x squared minus 3x plus 7 at x equals 2. If we did the long direction, we'd have to go through and find the first derivative using our h rule. From that, we get a slope formula. I'm going to go ahead and give you that answer is 2x minus 3. The next lesson will teach you how to do that. And then we would evaluate f prime at 2. Well, that would get us 2 times 2 minus 3, which is 1. Well, we can also do this with the calculator. There's going to be several ways we can do this. We're going to go to math, and we're going to go to deriv. So there's our nth derivative. There's our derivative function. And it's going to bring up a couple things. First thing it's going to ask for is what are we taking the derivative with respect to? We're taking the derivative with respect to x. Then we can type in our function. I'm going to show you 2 ways to do this. One way is just type in the function. So x squared minus 3x plus 7. And then we want x is 2. And if we hit enter, again, there's our 1. So we type that into our calculator and we get the same value. So dx of x squared minus 3x plus 7 evaluated at x equals 2. Another way to do this is we can actually put this into y equals. So let's put this into y equals. And we have x squared minus 3x plus 7. So that's our y1. It's in our function. So now we can go back to math. Actually, we want to quit out of that. We want to go back to math, do our derivative. Again, taking the derivative with respect to x. Now we want that y1 function. To do that, we're going to go to vars, and that vars button is right here. So we're going to go to vars. Then we want y vars, which is y variables is what that means. And then we want function. And then we want y1. Now, why would you want to do this instead of just typing it in? Well, there's going to be an advantage that we'll look at on the next slide. And again, we want to evaluate that at x equals 2. And again, there's our value at 1. So there's the derivative of a function. Now, we can also use the derivative values from the graph of the function. So I went ahead and graphed that, right? So that's in y1. So we can actually go ahead and graph that function. Let me zoom back out to a normal window. So here's my function, and I want to evaluate this at x equals 2. And to do that, I can go to second calc, right? And there's a bunch of stuff we looked at before, value 0, minimum, maximum, intersect. I want to look at dy dx. There's our derivative. And then you just type in what number you want. So I want x at 2, and then a screen should pop up, or there should be something prompting you. But I just typed in 2. And it's going to give us both the coordinate, there's x is 2, y is 5, but then there's also dy dx again, which is 1. So different ways to find the derivative using your calculator. Now let's look at some other things. We've talked about, again, the absolute value function. All right, it looks like this. We talked about its first derivative. That looks like this. Because to the right of 0, its slope is 1. To the left, the slope is -1. So here's our slope graph. Right, and that's the graph of our derivative function. Let's try using inderiv using this and see what happens. Because we know that this is not differentiable because of the corner, right? This is not a continuous function, so it's not differentiable. There's no derivative at 0. And so let's see what happens if we try that. So let's quit out of this. Let's go back to math, inderivative. And let's do with respect to x, we want absolute value, which is math number, absolute, plug in x. Then we want x with respect to 0. Now we know it's not differentiable, so it should get an answer that does not exist or is an error or something, but we actually get a value of 0. So what happened with that? Why does that work? Again, that's because it takes a little bit of value. So it takes a little bit of value from the right, a little bit of value from the left, and it averages those two values. So what are those two values going to average to? They're going to average to 0. Therefore, we have to be very careful. Again, you've got to be smarter than your calculator when you're plugging in stuff and know how your calculator works to make sure you're getting the right answer. What else can we use our calculator for? We can actually use our calculator to find the derivative graph. So let's use our calculator to find the graph of a derivative. So we've got, let's go back to y equals, and we're going to let our original function be x squared. Then we want to see what is the derivative graph of that function. To do that, we're going to go to y2. We're going to go back to math and get our inderivative. We want that derivative with respect to x. And we want, what do we want the derivative of? We want the derivative of y1. So we're going to go back to vars, y vars, and function, and we want y1. There's y1. And then we want x to equal x. Now what's this going to do? This is going to graph our original function, and it's going to find the graph of the derivative. And so let's see what happens. So the first one we know is a nice easy parabola. And then here's the graph of the derivative of the parabola. And again, as we saw in a previous lesson, that quadratic function is going to switch to a linear function. So there's the graph of the first derivative, the graph of all of the slopes of that parabola. Finally then, let's look at a theorem. The theorem says if then f has a derivative at x equals a, so in all points of the function, there's a derivative at x equals a, then f is continuous at x equals a. So the only way that a function can be differentiable is has a derivative at every single point. The only way it can have a derivative at every single point if f is continuous. What is the converse? Remember in geometry you talked about converse. Converse is flipping an if-then statement. So what would be the flip of our if-then statement? Well, that would say then if f is continuous at x equals a, then f has a derivative at x equals a. Now, is that true or false? If f is continuous along the whole function, then that means it has a derivative everywhere across the whole function. Well, that's false. And we can think of an easy counterexample because that's our absolute value function, right? There is no derivative at x equals 0. Even though it's continuous, there's not a derivative. So the theorem is true, but the converse is false. And finally, your homework for lesson 3.2. We're on page 114. You're doing problems 2, 4 through 26, 40 through 45, 11 through 16, you are graphing. 17 through 26, you're using the calculator. Have a good day, Maroons.